Hey everybody, and welcome back to Calc 3 Online. The plan for today is to actually talk about how to find the distance between line segments and planes in 3-space. But to start, I want to do something just kind of unrelated, but also important. So a thing you'll see in textbooks a lot of times, and something that we'll use here and there, is writing the vector form of a line segment. So we saw this before, and this would be the vector form of a line, right? So if we just take, so V0 here is like, kind of like our point vector. It's like a spot to sort of start in a sense. And if you do V1, right, minus V0, that would be like a direction vector, right? So if you do that direction vector and then you scale it, right, for all t, you get this yellow line. And so what I want to show first is just if we let's say t equals 0, right, that's going to mean that the above vector equation there would just reduce to the line, I guess we'll just call it L0, is going to equal just V0, right? Because that whole second term would go away. If I let t be 1, right, then I'm going to call this L1, would just be V0 plus V1 minus V0, or just V1, right? And so what this means is that at specifically t equals 0, right, that's always going to be our starting point. And t equals 1 would get us to, this other spot down the line here. And things like t equals 1/2 would be like literally a vector right here, kind of in the middle. So say you want to do a line segment, you want to define a line segment that just is between V0 and V1, then you can define like the line segment, I guess I'll call it line segment, as just V0 plus t times V1 minus V0, but only let t be part of the interval from 0 to 1, like inclusive there. Sometimes too you'll see this rewritten, you'll distribute the t, so you'll get V0 plus TV1 minus TV0, and so then they just group the V0s with a 1 minus t times V0 plus TV1. So I think that's the way you see it in your textbook. But this right here, it maybe at first seems kind of counterintuitive, like why you would get this 0 to 1 interval. But really, if you just go through kind of what 0 and what 1 gets you, you can kind of start to see why it really would just define a little line segment. So the main thing, like I said, I want to talk about today is the distance, like how we're going to calculate distance between things in, really this could be done in 2D, 3D, 4D, whatever you want. But it's pretty straightforward with vectors. And really it's just a good review of a lot of what we've been talking about. It's going to use tools from as early as just how do you find the magnitude of a vector and things like that. So in this problem, it says find the distance from the point B, which is 1, 0, 2, to the line L, which passes through the point A, 3, 1, 1. And they give you the direction vector of that line, which is negative 1, 1, 0. And so I think I'm a visual person. I always like to draw a picture. So I personally would draw a picture, and it does not have to be perfect because I don't want to try to scale this perfectly to the right spots and, with the actual coordinates. So I'm just going to draw like an arbitrary plane. Okay. And, we're doing a line. we're going to do a plane in a second, so that's why I was thinking that already. So say you have a line. There we go. This is the line L. And I'm just going to say this is point B up here. And line L has A on it. Okay. And we want to find the distance from B to the line. And that distance, distance always measured. The shortest way to get from B to L would mean that we'd have to drop down a line, right? The way I drew it there, and it'd be perpendicular. And so that's kind of, in my head, in the steps, that's sort of my arbitrary picture that sort of represents what's going on here. So we're going to need this vector, AB, but that's not too bad because we have we have the points, right? So we could just do subtraction. So if we have both the point A and the point B, we can just do B minus A to get the vector AB, right? So 1 minus 3, negative 2, 0 minus 1, negative 1, 2 minus 1 is 1. And then there's I kind of call just here a tool, right, that we've seen that would basically help me find this spot right at the base of B. And this picture right here, we've seen this before. It's probably not hard to guess that the tool I'm talking about is the projection, right? If we just project this yellow vector down onto L, right, we will get, we'll find exactly where this thing lands right here. So I'm going to set that up. So we have a direction vector for the line. I'm trying to think of colors to use. We'll do that. We'll do that one. So I'm going to call, so this V is in green, right? And if we project the yellow vector onto green, it'll scale it so it fits perfectly right there. That's the idea. So I want to project AB onto V. So AB, V. So we're going to have to do AB, all right, dotted with V over the magnitude of AB times the magnitude of V. And that's going to act as my scalar on the vector V. And so if we we just calculate that, right? We're going to have the dot product is going to give me, so if I did my mental math right, this should be a 1 on top, and then the magnitude of AB would be 4 plus 1 plus 1, so square root of 6. And then the magnitude of V would be 1 plus 1 is square root of 2. So that is the scalar times this vector here, negative 1, 1, 0. And what that really is, right, is a new vector that will land perfectly at the base of B, right? And really the idea, so we've done this. I mean, the way I do this is personally just with the Pythagorean Theorem. Now, you have a triangle problem, right? And if you want to figure out the blue distance there, right, we have this vector, so we can just do like an a squared plus b squared equals c squared argument and get the blue. Sorry guys, I was just looking at this and I realized I mixed my formulas up. I was using the cosine kind of angle between vectors formula. That's why I had these magnitudes. That's not what I want. I want this to be just v dot v down here. So it's actually going to be nicer. I was kind of worried for a second that this was working out kind of weird, but so this should just be v dot v, right? That's the projection formula. So v dot v would just be literally 1 plus 1, so we get a half there. That's a lot nicer. So the vector, the projection of AB onto V would just be negative a half, and then 1/2, and then 0. And so now we actually did need the magnitude of AB for the Pythagorean theorem. That was square root of 6. We need the magnitude of that projection vector, which is going to be just the square root of a half, right? Because it would just be 1/2 squared plus 1/2 squared. And then you can really just do, a squared plus b squared equals c squared. So if you do 1/2 the square root of 1/2 squared plus, I guess we'll call this b squared equals square root of 6 squared. I'm just going to use a calculator now. So I guess b squared is about 5.5, and then b is whatever, we'll just call it the square root of 5.5. And so this would be the actual distance. Maybe I'll do this in red. So this is the final answer, and that final answer is really, that exact distance from B down to L there. So I wanted to show you a mistake that a lot of times a student will make, and I would recommend you pause and ponder and think about why this is a mistake. So a lot of times what a student will do is, in a problem like this, they would find a normal vector. This is kind of hard to read, but a normal vector to the line, right? So 1, 1, 0 is definitely a normal vector to V, right? And that normal vector, right, if you draw it like this, it feels like, I could have that normal vector here, wherever I want. It seems like we could project this u vector over onto that, and that would just then be like a perfect, quick way to get, the distance if you just take the magnitude of the projection, right? So just like I'm doing here, U is now this AB, I renamed it U, but I'm doing my dot product of U and N, and then dot product of N with N. All that seems good. This number, 2.1, about 2.1, is not that number, which is it's a little hard to read, but that was supposed to be the square root of 5.5. And this is the part where I would definitely recommend you pause and think about it, because it isn't right to do that. The reason this is not correct is because in 3D space, right, and it's very hard for me to draw this, but I will try. But in 3D space, if you have a line, right, you can have all sorts of normal vectors, and we talked about this a while back, but there are lots of normal vectors that you could, in a sense, kind of think about like rotating around that green line there, and they're all going to still be perpendicular. It's like a huge assumption to assume that you just picked the right normal vector that sort of is in line with this, right? You can't just assume that red vector perfectly comes up here. In theory, you could maybe find it, but it's not likely that you would find it. So you really have to do it this way. You have to do a projection down onto the line, and then do like Pythagorean theorem. All right, I want to do this one now. So pretty similar, honestly, almost easier, I think, than the point and a line problem. So if you're doing a point and a plane, okay, but still, personally, I like to draw these things. So here's my plane, all right, and we have some point. I'm just going to say it's right here. And I want to find the distance. I'm going to label that B. I want to find the distance from B to the plane. And so, again, we're going to drop this down. has to hit 90 degrees perfectly. So in this case, so since this is kind of the reason this is a little easier is that we don't have that weird thing that we had down here, where we could, in a sense, think of infinite amount of normal vectors, rotating around that green line. Here, you're either going to have a normal vector that comes up out of the plane, or you could have like a negative that comes down. And so you can't have other ones. I mean, this is 2D thing living in 3D space, so you're only going to be able to go above or below. So this plane equation can give me the normal. Remember, we talked about some of that last time. So the normal, really just these coefficients, 1, 1, negative 1. And if you just pick a point in the plane, right? So we can find a point pretty easy enough. We could then make a vector. So I'm going to call that A, I guess. We could make a vector V that goes from like A to B. And we have a normal vector. The normal vector might be like bigger or something than the blue distance. But then I can project the red vector here over onto yellow, and it should perfectly scale it to the distance. So in this problem, you can actually just take the magnitude of the projection once we get that. So basically that's the idea. Now I'm just going to go ahead and kind of do that all. So to find a point in the plane, just make it easy on yourself. If I look at this equation, one that's kind of coming out, if I do 1 plus 1 is 2, minus 1 is 1. So I could call this point A down here just 1, 1, 1, right? And so that means vector V is going to just be 1 minus 1, 0, 0 minus 1, 2 minus 1 is 1. So that's my vector V. And then I'm going to project that onto the normal vector. So I'm not going to mess my projection formula up this time. The dot product of those two would be, let's see, negative 1 minus 1, so negative 2. And then the dot product of n with n would be 1 plus 1 plus 1, so 3. And so that's my scalar. So actually that scalar being less than 1 does tell me that it's kind of like this picture, where this yellow vector was bigger than the distance. So we're going to shrink it, and then if we find its magnitude, we'll be able to know exactly how far B is from the plane down here. And I did this out on a calculator. If you take the magnitude of that projection, you're going to get something that is about 1.15 units, whatever units you want to pick. That's it. Honestly, I think it's kind of easier than doing a point and a line, because you don't have to, you just have an extra step. You have to do this Pythagorean Theorem step, and you don't have to worry about that if you do it with a plane and a point. So I just want to do one more problem. I want to do the distance between two planes. And honestly, actually, I think for the sake of time, I might just show the setup and let you do the computation out. It really isn't that different. If I say I have this plane and this plane, I guess one thing to note too is that note that these planes actually are parallel, right? Because if you were asked to find the distance between non-parallel planes, you would just say 0, because they'd intersect somewhere. And since they're parallel, we can actually find the distance. It's actually a problem worth doing. And really the reason that we know they're, that I can see that they're parallel is just looking at the coefficients, right? The normal vectors for both of them are just the -5, 3, -2. And so they might have different, in a sense, kind of heights or something like that, right? They're like up at different spots, this and this. But the coefficients on x, y, and z are the normal vectors, or is the normal vector, and that those coefficients are the same. So the only difference here is, since you don't have a point to start with, you just find one. So pick a point in the purple plane, and you can just like do something, make it easy on yourself. Like maybe make, I'm looking at like, there's a 2 and a 14. So in my brain, I could make x be 0, y be 0, and then z would just have to be 7, right? 7 times -2 is -14. So that point for sure is in there. And then you can just pick a point in the second plane. And maybe in this one, I would do something like 5, 0, 0. Right? That for sure is in that plane. And then you basically just do the same problem you did before. You can create this vector. You can create a normal vector. And then you can just project onto that normal vector, and it will perfectly scale it. So this to this becomes the actual distance. So basically here, you still can do it the way we did it here, where we end up, setting up a projection onto the normal and then just finding the magnitude of that projection. So that is about how complicated you could ever see these. I mean, this kind of stuff becomes really important in, again, a lot of physics. There's a lot of problems where you need to calculate how far you are from a planet and different things like that. I took a celestial mechanics class, and we used to do these kind of things all the time, where we'd figure out distances of movement through space and all this sort of stuff. So it is something that we will see and have to kind of use this year.